Okay, today we are going to be evaluating limits analytically, and this is actually a little bit easier than what we did yesterday with looking at graphs, because that can get sometimes kind of confusing. And most of the time, analytically, all we need to do to evaluate a limit is to directly substitute the value of c into our function. So as you can see, the limit as x approaches c of f of x is just equal to f of c when c is continuous. So a couple of basic limits. If we have the constant function 3 and we're evaluating the limit at x equals 2, since the function 3 is 3 everywhere, no matter what that x value is, our limit would also be 3. For the second one, if we just have the function x, which is the line through the origin, if we have the limit as x approaches negative 4, we would just directly substitute in negative 4. So our limit is negative 4. Part C here, we have the function x squared, which is the basic parabola. If we have the x value of 2 for our limit, we just plug in 2. So 2 squared, which of course is 4. Okay, the properties of limits. A lot of the properties are similar to other kinds of properties that you have seen that have anything to do with scalars and functions in general. But let's say we have two different functions, f and g. The limit as x approaches c of f is a number L, and the limit as x approaches c of g is k. Then number one, the scalar multiple, b times f of x, the limit is just going to be b times L, since L was the limit for f. Sum or difference, still approaching c, we have f plus or minus g, and our limit is L plus or minus k. Product, f times g, which is going to be L times k. Quotient then should follow L divided by k, but just keeping in mind that k cannot be equal to 0, since that would be a undefined function. And the last one, the power, f of x raised to the nth power. We would just have L raised to the nth power. Limit of a polynomial. So like I said, since we are just doing direct substitution in this section, this is actually a lot easier than it looks. We are just going to take that 2, which was where we are evaluating the limit, and plug it in for x. 4 times 2 squared plus 3. 2 squared is 4, times 4 is 16, plus 3 is 19. So that was actually an example of a polynomial, which is the next definition we're talking about. If p is a polynomial function and c is a real number, then the limit as x approaches c of p of x is just p of c, which is what we just did. If we have a rational function r, which is given by two polynomial functions that are divided by one another, r is p of x over q of x, and c is a real number, then the limit as x approaches c of our rational function r is r of c, or p of c over q of c. Let's try one of those. Plugging in 1. I'm going to plug in 1 everywhere you see an x. So 1 squared plus 1 plus 2 divided by 1 plus 1. Top gives us 1 squared, which is 1, plus 1 plus 2 is 4, divided by 2. Our limit is 2. Finding the limit of a radical, so that's a power, anything raised to a fractional exponent, like the square root is the same thing as being raised to a 1/2 exponent. If we have the same sort of limit as x approaches c of the nth root of x, then what you're going to do is just put in c, same exact thing. Okay, now let's say we have composite functions. We have two functions f and g. The limit as x approaches c of g is L, and the limit as x approaches L of f of x is f of L. Then the limit as x approaches c of f of g of x, we've done composite functions before, is f of the limit as x approaches c of g of x or f of l. An example of this, because the limit as x approaches 0 of x squared plus 4 is 4, and the limit as x approaches 4 of the square root of 4 is 2, then the limit as x approaches 0 of the square root of x squared plus 4 is the square root of 4 equals 2. Now notice that we have combined both functions because we have the square root over our x squared plus 4 function. And if we have a square root of x plus 4 and we know that the limit of this is 4, that's how we got the square root of 4 here, and the square root of 4 is of course 2. Next example of the composites. Because the limit as x approaches 3 of 2x squared minus 10 is 8, and the limit as x approaches 8 of the cubed root of x is 2, then the limit as x approaches 3 of the cube root of 2x squared minus 10 equals the cube root of 8 equals 2. So we did the same kind of thing. We ended up taking the cubed root and putting it over our entire function for the first half. That's how we ended up with 2. Very similar. Okay, limits of the trig functions. These are going to be just as obvious as all of our other plug and chug, putting those c's into the function. It's going to be very straightforward. So number 1, sine of c. Number 2, cosine of c. Tangent of c, cotangent of c, secant of c, and cosecant of c. So even if we have trig functions, we can just plug in that c value that we're trying to find the limit at. Simple as that. Okay, let's say we're trying to find the limit of a function, but if we just plug the 1 in, we're going to end up with a 0 on the bottom, and we cannot have a 0 on the bottom. So what we need to do is figure out if we can factor anything. Now when you're factoring, just keep in mind that whatever's on the bottom, so in this case that's x minus 1, that's going to be one of your factors on top, otherwise this is a pretty useless process. So noticing that on top we have the difference of cubes, and if you didn't notice that, you can also do long division to find this whatever goes into x cubed minus 1, then we know that on top is going to be x minus 1 times x squared plus x plus 1, and the bottom is x minus 1. So like I said, you're definitely going to have one that cancels, and if you don't, you did something wrong. So once that cancels, we're left with x squared plus x plus 1. Obviously not when x is 1 though, because that would, going back to the original function, would give us a 0 on the bottom. And if we put the 1 in here, 1 squared plus 1 plus 1 is 3, so that's the limit of the whole thing. You are going to have a hole in your graph at 1. That's because of the undefined function, but you can still have a hole and have a limit at that point, as we saw in the first section. Okay, so again, in this case as well, when you put in the -3, you're going to get a 0 on the bottom, so you got to figure out something else to do. We are definitely going to factor. This is an easier function to factor since you don't have to do long division. The top is just going to be, again, one of them is going to be x plus 3. So if you want to start with that one right away, that would be a good plan. And since we're trying to get to a -6, we know that our second pair is going to be a negative. Now we can cancel the x plus 3's, and we're left with x minus 2. And when you put in -3 into x, you get -3 minus 2, which is -5. Okay, not bad. Now this rationalizing technique is not quite as obvious, and this is a process that you're going to have to know in the future, so just make sure that if you don't understand, this is what the video is for, is to come back and look at it again. So because when you plug a 0 in the bottom here, again, you still get an undefined function, but there's not really anything to factor, you have to think of something else to do. So what you're going to do is you're going to multiply by pretty much the conjugate of the top. It's not technically the conjugate, but it's as close to a conjugate as you can get. you're going to have the same thing, only you're going to have a plus 1. And you're going to multiply that on the top and the bottom. We have to do both because that's pretty much just multiplying by 1, and that's not changing our function at all. So when we have to FOIL this through, it does look like a pretty gross function to FOIL, but because they're opposites, we know that we don't have to do those inside terms because they're going to cancel anyways. So all we need to do is the first two, which is square root of x plus 1 times square root of x plus 1, which is the square root of x plus 1 squared, and minus 1 times 1. And on the bottom, we don't have to multiply anything through, and just leave it like that. So the square root of x plus 1 squared is just x plus 1 minus 1 all over that lovely function. Plus 1 minus 1 on top leaves us with just x. And since we have an x on the top and an x on the bottom, those two can cancel out. So we get 1 over square root of x plus 1 plus 1. So when we plug a 0 in here, 1 over square root of 0 plus 1 plus 1. The square root of 1 is 1 half. Okay, so making sure that we understand that rationalizing technique, this is the key. Multiplying by that conjugate term is going to get us somewhere good. Okay, the squeeze theorem. We have three different functions. When h is the smallest, g is the biggest, and f is right in between. And c is in all of these domains. So if the limit as x approaches c of our smallest function h is L, and that's also the limit of our biggest function g, then the middle function is going to have the same limit. So this isn't going to be exactly a picture of the squeeze theorem, but it's going to illustrate pretty well. So let's say that we have h is our smallest function. We don't hear smallest being the most negative in value. And then we have g being our biggest function up here. And we have f in the middle. And we're looking at the limit at this point here. Since g has a limit of 0 and h has a limit of 0 and f is right in the middle, it's also going to have a limit of 0 at that point. We're not going to use that too much, but just understanding what that means is going to be important. Okay, here's a couple of special trig limits. Now I'm not going to go through how we find them because it was pretty complicated, but I am going to tell you that you're going to need to know these. So the limit as x approaches 0 of sine of x over x is 1, and the limit as x approaches 0 of 1 minus cosine x over x is 0. So we don't need to know how you get those, just need to know that if you need to pull apart a function and you have this left over, that you know that the limit is 1 of the first and 0 of the second. And here's an example of how we're going to use one of those. So it's not obvious right away. It doesn't look the same as either of those, but we do know that tangent from trigonometry, tangent can be turned into sine over cosine. So if we turn tangent to sine over cosine, we still have that 1 over x on the bottom. We can keep it on the bottom with cosine. Then we can do a little bit of rearranging and we can make it look like one of those special trig functions that I just showed you. Sine x over x is a special one. So we know right off the bat that the limit of the sine x over x term is 1, and cosine of x, we know that the cosine of 0 is 1 as well. So if we have 1 times 1 over 1, it's of course 1. And last one. So what we're going to do to this function, we're trying to find the limit as x approaches 0 of sine of 4x over x. What we're going to do is multiply the whole function by 4. Now this is a little trick and it's going to help us set it up to be in one of those special trig terms. So we had the sign of 4x, and we're going to put a 4 down here as well. So now see how we multiplied by 4, but 4 on top and 4 on bottom, it makes 1, so we haven't changed the function at all. Now we're going to take this term 4x, and we're going to turn that into y, so that it's not going to be 4x, because that wasn't one of our special trig. We just wanted one term there. So if we're going to use y instead of x, we're going to need to do y approaching 0 side of y over y, because if we have that, this whole thing is 1. So then we have 4 times 1, which is 4. It's a little bit harder than anything you're going to have to do in your homework, but just recognizing how we did that, that multiplying by 4 over 4 is a good thing to know. Your homework is at the bottom here, and that was our section 3.